Welcome to this deep dive into the art of modern computer processor. At the core of every calculation, every decision, and every action, a computer takes is an arithmetic logical unit, which is known as ALU. In this presentation, we will explore the fascinating journey of how the additional single block ALU evolved into a highly complex pipeline execution units that power today's high performance processors. We will look at the overarching architecture, the dynamic flow of data, and finally, we will zoom in to examine the exact working mechanisms of the arithmetic logical shift unit. So, in the early CPU architecture, the ALU was built as a single block. It was highly centralized and responsible for processing every single mathematical, logical, and shifting instructions one after another. While elegant in its simplicity, it quicker became a bottleneck. As developer demanded more speeds, CPU needed to do more than one thing at a time. So this led to the evolution of ALU into the execution units. So there are three execution units: arithmetic units, logical units, and shift units, which work independently. This scattered layout is the foundation of superscalar architecture that allows the processor to execute multiple independent instructions concurrently with exactly the same clock cycle. So here there is an ALU core in which there are arithmetic units, logic units, and shift units. First, the input is passed through the control units, which then passes through the data path. From there, it is divided into multiple ALUs, which performs operations on them. Modern CPUs use superscalar execution units with multiple ALUs. With our units now specialized and scattered, we must effectively route data to them. This is where pipelining comes in. Think of pipelining like an assembly line in the factory. The instruction lifecycle is divided into distinct stages. Here, we can visualize the data flow. A packet of data is first received from the register file. Now and then it routes into the control unit, which acts as a brain, decoding the instruction to determine what needs to be done. Control unit then dispatches the data down the appropriate path towards one of the specialized execution units. When the data arrives at the execution unit, processing occurs. Visualized here by a distinct glowing pulse, instantly the computer result is forwarded down to the pipeline to, to the write back stage. Pipelining ensures that while one instruction is being executed, the another is being decoded, and yet another is being flashed, keeping all the parts of the processor constantly busy. So now let's zoom in closely on the individual execution units, starting with the arithmetic units or AU. This module is the heavy lifter for the mathematical operations, primarily handling integer additions, subtractions. In this data path, you can see two arrays of the bits representing binary numbers flowing into the unit where addition is performed. Array flows through a series of full adders because addition requires carrying over the bits from one column to the next. Modern ALU uses carry Modern ALU uses carry look ahead logic to compute these carries simultaneously across all bits, minimizing delay. For subtraction, the unit cleverly refuses the adding hardware by utilizing two's complement logic. It inverts the bit of the second number and adds a 1. A multiplexer at the output state guided by the control unit selects the correct final calculation to pass forward. Next, we move over to the logic unit. While the arithmetic units carry bits across columns to do math, the logic unit is entirely focused on bitwise operations. It performs functions like AND or XOR or NOR. These operations are crucial for low-level data manipulation like masking IP addresses or encrypting data. Notice the data flow here. It is strictly parallel. Each byte of the first operand lines up directly to the corresponding bit of the second operand. They pass through an array of logic gates side by side because there is no waiting for carry bits from neighboring columns. Logical operations are incredibly fast. The control unit sends a selection signal to the multiplexer, which simply closes the circuit for the requested operation. allowing only the correct results to flow through the output. So here there are two inputs and it passes to the control unit from where it is decided which operation needs to be performed like AND or XOR and NOR, which is decided by multiplier, and then the desired output is obtained. It is also known as bitwise operation or logic unit processing. Finally, we arrive at the shift unit. The ability to shift bits left or right is a fundamental important in the computer science. Shifting all bits in a binary number to the left by one position effectively multiplies the number by 2, while shifting the right divides it by 2. By doing this mechanically is much faster than running a mathematical multiplication algorithm. Watch the data path in action. During a logical shift left, the entire array of the bit steps aside. As they move, observe the visual clues. The bit pushed off the far left edges are discarded and gently fade into nothingness. Simultaneously, you can see a new glowing zero bit appearing on the right side to fill the newly created empty spaces. After alignment, the multiplexer routes the shift data out and completing the process. Ultimately, what began as a bottleneck monolithic block has transformed into a masterclass of parallel engineering. By breaking the ALU into specialized arithmetic, logical, and shift units and coordinating them with a continuous piped data flow, modern processors achieve the astronomical speeds we rely on every single day. And thank you for joining us on the visual journey through the computer data path. My name is Ghoniya Dhyey and I am from CSPIT and my ID number is 240024.